We've all seen it. You're on Amazon, looking at a new phone. You added it to your shopping cart, and before you checked out, it suggests customers who bought this also bought a matching accessory. It feels like magic, doesn't it? Or maybe a little bit like mind reading. But as engineers, we know it's not magic. Behind that seamless recommendation is a data pipeline that was designed, built, and maintained by data engineers. It collects your clicks, processes your purchase history, and feeds it into algorithms for those spot-on suggestions. In this video, we're going to look at what really happens in those three phases: design, build, and maintain. And we'll use Amazon's personalized recommendation system as our guiding example. Let's start with design. In this phase, you're the architect. Your job is not to write code yet, but to make big decisions that will determine how fast data moves, how reliable the system is, and how expensive it will be to run. One of the first trade-offs you have to juggle is between latency, which is how fresh the data is, and structure, which is how strictly the data is organized before it's stored, and when that structure is applied. Latency and structure are tightly connected. If you want very low latency near real time, you usually have less time to clean and reshape data before it's stored. If you want very rich structure up front, which requires lots of cleaning, validation, and reshaping, you typically accept higher latency because all that work takes time. We'll go much deeper into structure later in the series when we talk about ETL versus ELT and schema on write versus schema on read. In this video, we'll stay focused on the first part of that trade-off, which is latency and how it leads to the choice between batch and real-time architecture. Let's focus on latency first because it's the heart of our Amazon example. So, what is latency? Latency is the time between the moment a data event happens in a source system. For example, a user adds an item to the shopping cart, and the moment that data is available to be queried in your analytics system. For example, when a recommendation model or dashboard can see it. In other words, latency quantifies the freshness or age of the data. The lower the latency, the closer you are to real time. And this requirement for latency directly influences the system architecture you choose and the cost required to maintain that system. At design time, one of the most critical decisions is, do we build this as a batch system or a real-time system? In a batch architecture, data is collected over a fixed period of time and processed all at once on a schedule. For example, you might have a job that runs every night at 2 a.m. It reads all yesterday's orders, clean and transform them, then loads them into the data warehouse. In a real-time architecture, data is processed continuously as events happen. As soon as the user clicks Add to Cart, that event flows into your pipeline immediately, and your system reacts in seconds or even milliseconds. Now, the choice between batch and real-time doesn't just affect when data arrives. It also dictates which software components you'll need, how complex the system is, and how much you'll pay for infrastructure and maintenance. So ask yourself, do we need that recommendation to update the second the user clicks Add to Cart? In the Amazon-style shopping experience, the answer is yes. It wouldn't make sense to rely on a batch job that runs at night to recommend products to a customer shopping at 2 p.m. By the time the nightly job runs, the customer is long gone. That pushes us strongly toward a real-time architecture for this use case. But this decision has consequences. If you choose real-time when it isn't needed, you can drive the cost unnecessarily high. If you choose batch where freshness matters, you end up with stale data that isn't useful. This is why the design phase is so critical. The wrong architectural choice here can lead to a system that either doesn't solve the business problem or costs far more than it should. We'll dive much deeper into latency and cost trade-offs in later videos. For now, just remember, in the design phase, data engineers decide how fast data needs to move and that choice shapes everything that follows. Once the design decisions are made, we move to the build phase. Now we write the actual code and assemble the components that physically move data from A to B. Continuing our recommendation example, here's a simplified view of what that looks like. First, we need to capture the moment the user clicks Add to Cart. This is often done with a message bus or event queue. Systems like Apache Kafka, AWS Kinesis, or similar tools. The application sends an event as a JSON payload. That event is pushed into a message bus. The bus acts as a high-speed buffer, holding events temporarily so other services can read them. This decouples the front-end application from the rest of the pipeline. The app doesn't need to know who will process the event. It just needs to publish it to the queue and move on. Next, a service we build. This could be written in Python, SQL, or some combination. Subscribe to that stream of events. Every time a new Add to Cart event arrives, this service reads the event from the queue. It looks up relevant data, such as the user's past purchases, what similar users bought, and product relationship. For example, t-shirt with matching accessories. It then runs the recommendation logic or passes data to a machine learning model. And finally, it sends the resulting recommendation back to the application. From the user's point of view, they click Add to Cart, and within a second or two, they see the customer who bought this also bought section on the page. Under the hood, a pipeline just fired. An event is captured, data moved, logic executed, and result is returned. As data engineer, your job in the build phase is to implement these components, ensure they can handle the required traffic, and make them observable so we can monitor and maintain it. The third phase is maintenance. This is where the job shifts from building it right to keeping it running correctly over time. It's tempting to think the biggest risk is the pipeline fails or the website crashes. Those are serious, but often not the most dangerous failure. The real nightmare is this. The pipeline succeeds technically, but silently produces garbage data. This kind of failure happens when the data itself changes in ways your pipeline wasn't expecting. For example, imagine the price column in the source database silently changes from US dollars to euros. The data type might be the same. The column name is the same. Your pipeline runs successfully with no errors. But the downstream report and model now interprets 100 euros as 100 US dollar. Revenue dashboards and financial reports are now wrong. Machine learning model trained on this data are learning from incorrect signals. Technically, everything is green, but in reality, the business is making decisions on corrupted data. That's why a robust data pipeline isn't just about moving data. It also needs checks that validates assumptions like, are value within expected ranges? Schema monitoring that detects new columns, remove columns, or type changes. For example, if the number of daily transactions suddenly drops by 90%, or if the average price unexpectedly doubles overnight, the system should raise an alert, notify a data engineer, and in some cases, stop bad data from flowing further downstream until someone investigates. The goal in this phase is to make sure that when data quality fails, and it will at some point, the system notices it quickly and someone can fix it before the business relies on wrong numbers. So, to recap the life cycle of our recommendation pipeline, first, design. Decide, do we need batch or real time? Define latency requirements and how strictly we need to structure the data. Understand that these choices drive cost, complexity, and data freshness. Next, build. Implement the components such as event capture via message bus or event queue and processing logic using Python, SQL. And finally, maintain. Monitor for silent failures like schema change, unit changes, weird spikes or drops in data. Add checks, tests, and alerts so that breakages are caught early and bad data doesn't quietly poison reports and models. When you do your job right as a data engineer, no one notices the pipeline. The customer just sees a perfect product recommendation. The CFO just sees a clean, accurate financial report. And the data scientist just gets the data set they need. It doesn't look like magic, but it feels like magic to everyone else. In this video, we focused on the life cycle of design, build, and maintain, but we skipped over a big question. What exactly do we mean by latency? And why can't we just make everything real time and call it a day? In the next video, we'll break down the two different kinds of latency you need to care about as a data engineer. Data latency, how fresh the data is, and query latency, how fast reports and dashboards respond. Why these two often work against each other, and why stakeholders often say fast, but mean very different things. If that sounds interesting, don't forget to like, subscribe, and turn on notifications so you don't miss the next part of this series. See you in the next video.